Of our series on numerical methods in civil engineering, we will complete our discussion of the conjugate gradient method by talking about nonlinear conjugate gradients, and we will start our discussion of partial differential equations. So, up till now we have considered the conjugate gradient method exclusively for finding the minimum of a quadratic form, right? We have not looked at the general nonlinear problem. However, with some modifications, the conjugate gradient method can be used for general nonlinear functions f of x, basically to find the minimum of a general nonlinear function f of x, provided the gradient can be calculated at every point in our domain of interest, right. So, provided we can calculate grad of f of x, we can still use the conjugate gradient method for general nonlinear problems with some changes. For general nonlinear functions, the conjugate gradient algorithm has to be modified to enable it to work. What are the modifications necessary? Well, first of all, the residual can no longer be evaluated by Ri is equal to minus Ai, because there is no constant matrix A anymore, right. To find the minimum of a general nonlinear function f of x, we need to find a root of the nonlinear function gradient of f of x is equal to 0. So, we want to find the value of x such that gradient of f of x is equal to 0. If the minimum corresponds to x, that is x is a root of gradient of f of x is equal to 0, then as we go towards that root at iterate xi plus 1, the residual Ri plus 1 can be written as the gradient at the root, at the exact root, minus the gradient, the current gradient at xi plus 1, and since we know that we are at the exact root, the gradient is got to be 0. So, gradient of f of x is going to be 0, and so we get minus grad of f x I plus 1. So, that is going to be my residual. So, that is one thing. So, we cannot calculate the residual using our previous formula. So, we have to calculate the residual directly from the gradient of the function. In addition, it is no longer possible to write a closed form expression. Again, I have a typo for the step size, as in alpha I is equal to Ri transpose Ri divided by di transpose a di, right. We cannot anymore calculate a closed form expression for this step size. So, instead we compute the step size by solving a one dimensional minimization problem. And what is that one dimensional minimization problem? Well, it basically requires us to find the value of alpha in the search direction d, which is going to minimize my function f x I plus alpha I di, right. But this f x I alpha di is fixed, right. I am going along a particular search direction. So, di is fixed for that iteration, right. So, that expression, that function f of x I plus alpha I di becomes a general polynomial in alpha, right. It becomes a general polynomial in alpha, and so we are required to find the value of alpha which minimizes that function. Also recall that when the conjugate gradient method is applied to a quadratic form, so that was the second change that we need to make, right. First of all, the residual has to be calculated differently, the step size has to be calculated differently. Thirdly, the Gram-Schmidt coefficients are different. Why? Because when we use the conjugate gradient method for quadratic form, the Gram-Schmidt coefficient beta ij, we evaluated it as beta ij is equal to minus Ri transpose a dj divided by di transpose a dj, and we took advantage of the Krylov structure of the subspace formed by the search directions to simplify the expression for beta ij to get beta ij equal to minus Ri transpose Ri by Ri minus 1 transpose Ri minus 1, right. And we found that only one beta ij is required, right. Only one beta ij is required. The others we do not need to enforce because they are automatically orthogonal. The previous residuals are automatically, the previous search directions are automatically orthogonal to the current residual. In the absence of a constant coefficient matrix A for the general nonlinear equation, how to choose beta ij becomes an open question. There is no definitive solution to that. Still people are doing, people are proposing different formulas for that, right. One option is to just use the expression which we use for linear conjugate gradient, right, for conjugate gradient applied to the quadratic form. That is, we use this expression for beta ij, right. So that is known as the Fletcher-Reeves algorithm. The Fletcher-Reeves algorithm, which is identical to that used for the quadratic form, and then there is the Pollack-Reber formula, which is a slight modification, which gives beta ij is equal to Ri transpose. If you compare these two, you can see that it is slightly different. This is this, and that's that, right. So it is slightly different, right. Then there is the other formulas. For instance, there is something called the Heston-Steinfeld formula, There are other formulas also, but these are the main ones. Now, the Fletcher-Reeves algorithm, when is the Fletcher-Reeves formula going to work best? Well, it is going to work best near the solution. Why is it going to work best near the solution? Because near the solution, whatever be my nonlinear function, it is going to behave pretty much like a quadratic, right. So when it becomes a quadratic, then my linear conjugate gradient applies exactly, right. So near the solution, that Fletcher-Reeves formula is going to work well, because the function behaves quadratically, right. Any function near its root, you can pretty much approximate it very well by quadratic. So the Fletcher-Reeves formula is guaranteed to converge if the starting point is close to the solution. Why? Because close to the solution it is going to be a quadratic. The behavior is going to be more or less quadratic, right. So close to the solution, the Fletcher-Reeves formula, if you start your iteration with a starting guess which is close to the minimum, then the behavior of the function near the minimum is pretty much quadratic, right. The Fletcher-Reeves formula is going to converge very well. But since near the minimum, the general nonlinear function f of x is accurately approximated by quadratic. Since for a quadratic form, the Fletcher-Reeves formula part of the linear conjugate gradient algorithm is guaranteed to converge, this is obvious, right. However, far from the minimum, the function may be very different from a quadratic. In that case, convergence is by no means guaranteed. If we use the Fletcher-Reeves formula for a general nonlinear function and we start far away from the true solution, then there is no guarantee that we are going to converge, because the behavior is nowhere near quadratic, right. The Pollack-Reber formula for beta ij is found to converge in most cases. It converges in most cases irrespective of the starting point, right. Though in rare situations it can result in the algorithm going into an infinite loop and failing to converge. Basically it starts cycling, right, then it cannot converge, right. Since neither formula is foolproof, the restart concept is indispensable in nonlinear conjugate gradient iteration. This is probably the most important concept, the restart concept, when it comes to nonlinear conjugate gradient iterations. Basically it means that the effort to create search directions conjugate to the previous search directions has to be abandoned at certain point. When we think that we are no longer converging, right, or we have exceeded n number of iterations, right, we know, recall that the conjugate gradient algorithm, if it's an n dimensional space, we construct n conjugate directions, right. So there are only n conjugate directions, right. So suppose my iteration takes more than n, it goes to n plus 1, right, it still doesn't converge. Then obviously the new directions that I am using, they aren't conjugate directions, right, because I have already exhausted all the possible conjugate directions. N conjugate directions have already been exhausted. So there is no point. So I am no longer doing the conjugate gradient method. So at that point I stop my iteration and restart my algorithm. How do I restart? Well, I calculate the current value of the residual, set it equal to the search direction like I did when I started my conjugate gradient, and then I start the iteration again, right. Basically it means abandoning the effort to create search directions conjugate to the previous search directions and starting afresh, assuming the current values of the residual vector to constitute the new search direction D0. So, convergence with the Pollack-Ribet formula can be guaranteed if we restart whenever the Pollack-Ribet formula predicts a negative value for the beta ij. Suppose I get a Pollack-Ribet beta ij which is negative. So, at that point I know that my Pollack-Ribet formula is giving arbitrary result. So, I better abandon it and start again with the current residual as my first search direction. Since the conjugate gradient method can generate only n search directions, where n is the problem dimension, an obligatory restart should be performed after n iterations, right. The following is a summary of the nonlinear conjugate gradient algorithm. So, we start with initializing our initial search direction D0 with the residual at R0, right. Then for each iteration, we find the alpha that minimizes f of xi plus alpha I di. At this stage I assume I already know di, right. So, I find the minimum of this function nonlinear function in alpha, right. Once I find alpha, I update the new iteration, the new iterate value xi plus 1 is equal to xi plus alpha I di. So, once I know xi plus 1, I calculate the gradient. Now, that's some strange notation, right. So, I do not need that f prime here, right. I already have that gradient, right. So, again I apologize for the typo. So, I find gradient of f at xi plus 1. So, I calculate the residual at Ri plus 1. Once I calculate the residual, I either use my Fletcher-Reeves formula or my Pollack-Ribet formula to calculate the new beta ij. Once I get my new beta ij, I find out by new search direction, right, and I make sure that any time I exceed n iterations, I start again, right, from here, right. You can see that this Pollack-Ribet beta ij, I have a max here. This is to ensure that it is never negative, right. If it is negative, then it's bad, right. So, if it's negative, it's 0, right, and that tells me that I better restart, because I am not going to use a new search direction, get a new search direction. So, convergence for nonlinear conjugate gradient. Summarizing conjugate gradient, nonlinear conjugate gradient, we are guaranteed to there is no guarantee, right, there is no all the convergence criteria we obtain for the linear conjugate gradient, that just goes out of the window, right. There is no guarantee, right. The less quadratic the function f of x, the faster is the loss of conjugacy of the search directions, right. So, we are guaranteed to converge in n iterations if my search directions are conjugate. If my search directions lose conjugacy, no guarantees, right, and here there is no guarantee of conjugacy at all, right. Also, the recall, this is a general problem for all general nonlinear equations, which is that all general nonlinear equations, there is no unique minimum, no global, it is very hard to reach a global minimum, right. So, you get to the local minimum to which you start closest, right. So, will converge, if we converge, we are going to converge to a local minima depending on our starting point. And as mentioned, a generalized line search may be required to choose the step size alpha to minimize f of xi plus alpha I di in direction di. So, I have talked a little bit about the generalized line search problem. The objective is to find the zeros of d alpha f of xi alpha I di. So, I want to minimize f of xi plus alpha I di. So, that how do I minimize? I set the derivative with respect to alpha to 0, right. So, that's just the gradient. You calculate the gradient and you take the projection of that in the d direction, right. You take the projection of that in the d direction, you get a polynomial in alpha, right. You get a polynomial in alpha, and then you can use the Newton-Raphson method. So, this is a polynomial, a general polynomial in alpha. You can solve it using the Newton-Raphson method to solve for the zeros of this polynomial in an iterative fashion. So, how do you do that? Well, you expand the function f of xi plus alpha I di in Taylor series about xi up to the quadratic term. So, you write f of xi plus alpha I di approximately equal to f of xi plus alpha gradient of f transpose alpha di gradient of f transpose xi plus alpha square by 2 di transpose gradient of xi di, right, this up to quadratic term. And then we have to find alpha I such that why do we do that? I did that because this offers us some insight into the convergence of the conjugate gradient method. Let us follow through and we will see, right. So, from this equation we set this to 0, we take the derivative with respect to alpha and we set this to 0, right. So, we get grad f transpose xi di plus alpha di transpose, this is the Hessian, right, the second derivative, right, Hessian di equal to 0, right. And so, this is an equation which I can evaluate to obtain my alpha. And what is that? So, denoting grad f transpose xi at alpha equal to 0 as the Jacobian J and grad square f xi at alpha equal to 0 as the Hessian H, we have to solve for the following equation for alpha I, which is this. Now, compare this equation with the equation I had for the linear conjugate gradient, and that is going to be very revealing. Or did I have that equation right there? Yes, I had that equation right there. This was my equation for the linear conjugate gradient. So, what do I have? Let us compare terms. So, this is J I transpose, right. J I transpose I know is nothing but this, right, it is the Jacobian. What is this? This is nothing but the residual, right, we saw that, right, gradient of f, that is very similar to the residual, right. Then I have di here, but I have ri here, but we know that we get the search directions di from the residual ri, right. So, that is also very similar. Look at the bottom, we have di transpose here, then we have the constant matrix A and we have di. So, instead of A, the major difference is that instead of A I have the Hessian, here, and so that is, so the only difference is that in case of linear conjugate gradient the Hessian is a constant matrix A. Here the Hessian is a variable matrix, right, it is a function of where I am, it is a function of xi, right. So, that is the difference. So, this is exactly what I said, right, so we can see there is a distinct resemblance of this equation to the linear conjugate gradient if H can be regarded as an equivalent of the constant coefficient A in the linear case, right. So, for nonlinear conjugate gradients, the search directions are conjugate if they are conjugate with respect to the Hessian matrix, because the Hessian here plays exactly the same role as the A matrix. So, if the directions are conjugate with respect to the Hessian matrix, right, then the conjugate gradient method is going to do well, it is going to be very close to its behavior in the linear for the linear conjugate gradient situation, right. The only problem is, however, unlike linear conjugate gradient, the H matrix, which in case of linear conjugate gradient is a constant matrix A, is not constant. It varies from iteration to iteration, and the faster the variation of H, the faster the search directions lose conjugacy. The more constant H is, the greater the chances of my retaining conjugacy. And this also tells me by closer to the solution I have better convergence, because closer to the solution my function is going to behave like a quadratic. If it is going to behave like a quadratic, the Hessian got to be constant, right. So, closer to the solution my Hessian is going to be constant. So, there is a better chance of my conjugate gradient directions maintaining conjugacy. If they maintain conjugacy, all the good things follow, right, all my convergence properties they follow, and I am assured to converge, right. The closer xi is to the solution, the function f can be more accurately approximated by quadratic. when the Hessian approaches a constant matrix and the iterations become similar to linear conjugate gradient iterations, right. Let us talk a little bit about preconditioning for the nonlinear conjugate gradient method. As with the linear conjugate gradient method, convergence for the nonlinear algorithm can be improved by preconditioning, right. We said that if we multiply by coefficient matrix with a certain operator, a certain matrix, or we operate on that coefficient matrix with a combination of matrices, right, and we get a coefficient matrix which has a condition number which is smaller than my original coefficient matrix A, then I am going to get better convergence, because the convergence of the conjugate gradient method depends on the how well conditioned my coefficient matrix is, how close my eigenvalues are to each other. So, best situation is when the eigenvalues are like they are grouped together, right. When the eigenvalues are grouped together, that gives us the best convergence, situations like that, right. So, this is all an attempt to improve the condition number of my coefficient matrix. So, how do we condition the coefficient matrix in case of nonlinear conjugate gradient? Well, sometimes what people do is to use the Hessian matrix, right. Take the Hessian matrix, throw out all the off diagonal terms and keep the diagonal terms. If you keep the diagonal terms and if all the diagonal terms are positive, then I am assured that my preconditioner is symmetric and positive definite, right. So, the condition was that the preconditioner has to be symmetric and positive definite. So, if I do that, then I am assured that that's a valid preconditioner, right. If we can't do that, well, just don't do any preconditioning. Never try a preconditioner where you have a negative element on the diagonal, because that is a sure prescription for divergence, right. So, that is all I had to say about the conjugate gradient algorithm, and that winds up our discussion on gradient based methods, and it also winds up our discussion on methods for equation solving. So, that is all I am going to talk about equation solving for the rest of this course. For the rest of this course, we are going to focus on how do we get those equations. Those equations that we get, those matrix equations that we try to solve, well, how do we get them, right. So, up till now we have concentrated on methods of solving linear and nonlinear systems of equations. As mentioned in lecture 1, these systems of equations arise from mathematical models of physical phenomena. In civil engineering applications, more often than not, the mathematical tool that best models these phenomena are differential equations, right. So, they establish relations between rates of change of quantities of physical interest, for instance displacement, velocity, density, pressure and things like that, how these things vary typically in response to some external excitation, right, external excitation or flux or whatever. These physical quantities often depend on more than one spatial dimension as well as time, right. Hence, the rates of change, that is the derivatives, are most often with respect to multiple spatial dimensions as well as time, right. So, these derivatives are derivatives of multiple independent variables, right. Deal with and so we come up with relations between partial derivatives and hence with partial differential equations. Now, partial differential equations is a vast subject. Analytical treatment of partial differential equations, that there are entire courses which people teach it for those things, right. I cannot even attempt to try to cover any portion of it with any reasonable degree of coverage during this course. So, but I do think that when someone is trying to solve partial differential equations numerically, it is very important that at least we understand the basics of partial differential equations, right, and at least we understand some basic analytical tools that people can use to solve partial differential equations, right. So, in the next few lectures we will talk about some simple analytical tools for solving partial differential equations which are valid for a wide range of partial differential equations, before actually embarking on how to do the numerical formulation, right, how to get from the partial differential equation to the matrix equation, right. That step we are going to postpone it for some time and talk about some more a brief introduction to analytical methods for partial differential equations. So, many of these partial differential equations that arise in civil engineering applications are of second order, and the most general second order partial differential equation in two independent variables can be written as the following: f of x1 x2 phi x1 phi x2. So, you can see that this is a second order partial differential equation. Why? Because the highest derivative is of order 2. So, the subscript denotes derivative with respect to x1 and x2, right. The highest derivative is of order 2, right. So, but this function is a perfectly general function. There is no guarantee that that is going to be a linear function. It can be a nonlinear function of the derivatives, right. But when it comes to nonlinear partial differential equations, we are not even going to try to solve them, try to talk about analytical solutions. We are going to do numerical methods. That is the whole purpose of this course, right. But at least for linear partial differential equations, we want to look at some common analytical methods that can be used for solving them, right. The above equation can be linear or nonlinear. Nonlinear partial differential equations arise in civil engineering applications, but their analytical solution is complex and often impossible. They have to be solved numerically, giving rise to systems of nonlinear matrix equations, which we have already seen how to solve, right. However, the mathematical process of obtaining the governing differential equations of a physical problem and then transitioning from the differential equations to the matrix equation is very common for both linear as well as nonlinear phenomena, right. So, if we understand that basic mechanism, I mean it is common to both linear and nonlinear equations, right. The equations themselves are different, the solution methods, the matrix solution methods are different, right. We have seen that, right. Newton-Raphson, conjugate gradient, steepest descent, those are all for nonlinear equations, while straightaway Gaussian elimination or can be used for linear equations, right. So, the solution methods are very different, the equations are very different, but to go from the equations to the solution method, the process is not that different, right. Some differences, but not that different, right. So, the process we are going to look at for linear equations, right. Hence, for ease of understanding, we will examine this process for linear partial differential equations, right. So, the previous equation that we showed, that was for the general nonlinear equation, the second order nonlinear equation. If it is a linear equation, then in two variables, then it has this form. This is the general form of the linear equation, where now a, b, e, d, e and f are all constants, right. If a is a function of either of the independent variables, or if for that matter any of these constants are functions of either of the independent variables, we are no longer going to have a linear equation, right. So, this is what makes it. Phi is the physical quantity of interest whose functional dependence on the two independent variables x1 and x2 are what we seek to find, right. So, we are given this equation, and we want, if we want to solve it analytically, we want people to tell us what is the functional form of phi in terms of x1 and x2, right. A, B, F are constants with no dependence on the independent variables x1 and x2, otherwise the relationship would be nonlinear. For different values of the above constants and for particular choices of the independent variables, we get the following 3 PDEs, right, which are very sort of generic PDEs, right. So, what are they? Well, when one of the independent variables is time and the other is space, remember that we are now considering only 2 independent variables. There is no restriction on that. We can consider second order partial differential equations in more than 2 independent variables, but for the timing, let us consider that we are considering 2 independent variables, right, and one of them is space and the other is time. So, if that is true, and then these constants A, B, E, D, E and F, they this should be C, again this is a typo, right, this is a C, right. So, if that is so, these functions have the following values: A is equal to 1, B is equal to 0, C is equal to minus 1 by C square, which is a little little cumbrous notation, but this C is very different from this C, right. This C is the wave speed, right. But since we are talking about the wave equation, this is the wave speed. I did not want to change the symbol because this is sort of universal for wave speed, and the D, E and F are equal to 0. So, all the cross terms are, there is no cross term, and also the single derivatives also vanish, right. So, in that case, this equation becomes my wave equation, right. This equation becomes the wave equation. For A equal to K, K being the diffusivity, right, K being the diffusivity, E equal to minus half, D, C, B and F equal to 0, we get the diffusion equation. So, this equation, if for civil engineers, this is basically your equation of motion, right. This is exactly the equation of motion which you encounter in mechanics, right, solid and structural mechanics. This is the equation of motion. This for you, for civil engineers, this is probably, you do not encounter it too much in structural mechanics, but you encounter it in heat transfer, right, when you consider heat flow, right, diffusion of heat, right, if phi becomes the, right. So, in that case, then that becomes the heat transfer equation, right. For transient heat transfer, that is the equation. When the evolution of phi does not depend on time, so you can see here we have independent variables t and x, time and spatial dimension. When the evolution of phi does not depend on time, that is, the independent variables are spatial variables, we get for A equal to C equal to 1 and B equal to D equal to F equal to 0, Laplace's equation, right, Laplace's equation, which Laplace's equation is nothing but the wave equation if I ignore the transient term, right. So, if we solve the equations of motion, instead of solving the dynamical equations of motion, if we make the quasi-static assumption, we say that my solution, my phi, my variable phi is varying so slowly that del 2 phi del t square is very small, right. So, this part becomes 0. So, I get this, right. So, that becomes that. So, I get Laplace's equation, right. So, these are 3 main types of equation, and we will see later on, slightly later on, that they have they map on to certain things which are known as the canonical forms, of second order partial differential equations. So, each of these equations is a representative of a canonical form of the second order partial differential equation. So, for 2D or 3D problems, the number of independent variables increase. The 3D wave equation, for instance, is this, right. So, instead of x1, I have x1, x2, x3, right, second order partial derivatives with respect to x1, x2, x3, which I can write as 1 by c square del 2 phi del t square is equal to Laplacian of phi. Well, that is the Laplacian operator, right. So, the 3 partial differential equations we considered, like the wave equation, the diffusion equation and Laplace's equation, are model most of the physical phenomena of interest in civil engineering, there are also instances of the three canonical forms of equation star, which is this equation, right. So, they are examples of the three canonical forms of my general second order linear partial differential equation. How can we get the canonical forms? Well, you can get the canonical forms by transforming linearly the variables in star, right, by doing a linear transformation. So, how do we do that? Well, we first group the terms involving the second derivatives in star and treat them as arising from the action of a linear operator L acting on phi. So, these are the terms which involve the second derivatives, right. Second derivative with respect to x1, with respect to x2, and this is the cross term. And we say that we get this by the action of some linear operator acting on phi, right. Why is it a linear operator? Well, because it satisfies linearity. L of phi 1 plus phi 2 is equal to L of phi 1 plus L of phi 2. L of alpha phi is equal to alpha L of phi, right. So, it satisfies definition of linearity. So, this is like a linear operator, right. And I rewrite this operator in this way. So, I have this row matrix, I have this little row matrix del del x1 del del x2, right, and then I have this little 2 by 2 matrix A B B C, and then I have this column matrix del del x1 del del x2. So, you can see that if I carry out this matrix vector, the vector matrix vector multiplication, I am going to get exactly that equation, right. So, next we consider a transformation of variables, right. We say that we are going to go from x1 x2 to another set of variables y1 y2, right, and this T is my transformation matrix. So, y is equal to T of x, right, or y1 y2 is equal to, so I wrote out the transformation matrix in full form. So, just let us think of it just as a transformation from x1 x2 to y1 y2. So, it is clear that using the chain rule del del x1 equal to del del y1 del y1 del x1 plus del del y2 del y2 del x1, right. And what is del y1 del x1? That is nothing but T11 from this equation, right, because this equation gives me y1 equal to T11 x1 plus T12 x2. So, del y1 del x1 equal to T11, del y2 del x1 is equal to T21, right. So, that gives me del del x1 in terms of del del y1 del del y2. Similarly, I can get del del x2 in terms of del del y1 del del y2, right. So, what do I get? So, I can write del del x1 del del x2 phi is equal to this T1 T21 T12 T22, just grouping them together into a matrix again, right. So, basically I am rewriting these last two equations as matrix equations, right. T11 T21 T12 T22 as del del y1 del del y2, which is nothing but T transpose del del y. If del del y I denote this column vector del del y1 del del y2, this is equal to T transpose del del y, because my T had T11 T12 T21 T22, and this matrix has T11 T21 T12 T22. So, this I get a relationship between the partial derivatives, right. Using the above transformation of variables, what does L phi become? Well, L phi becomes, let us look at L phi again. So, it is del del x1 del del x2, right. So, that I can write as del del y1. So, this is just the transpose of this equation, right. So, this becomes del del y1 del del y transpose t, right. So, this becomes del del y transpose t, and then I have my little matrix A B B C. So, that remains the same, and then I have del del x1 del del x2, which I know is nothing but T transpose del del y, right. So, I get it in this form, right. Now look at this matrix A, B, B, C. This matrix is symmetric, right? This matrix is symmetric, and because it is symmetric, I know that its eigenvalues can't be imaginary numbers, its eigenvalues got to be real numbers, and its eigenvectors form an orthonormal basis, right? They form an orthonormal basis. So I can do a spectral decomposition of that matrix. I can find its eigenvalues, I can find its eigenvectors, and I can write that matrix A, B, B, C, denoting it as M, right? Denoting it as M, I can write it as T M T transpose, right? So that's, I'm just rewriting that equation, right? I'm just rewriting that equation after replacing this A, B, B, C by M, right? But then the interesting part is that follows, right? Because M is a symmetric matrix, I can do a spectral decomposition and I can write it as V lambda V transpose, right? Where V is a matrix whose columns are the eigenvectors of M, right? And lambda is a diagonal matrix whose diagonal elements are the corresponding eigenvalues, right? So this is a similarity transformation applied to symmetric matrices because it's symmetric, so V transpose instead of V inverse, right? So M I can write as M is equal to V lambda V transpose, right? And then so now M becomes, so now L phi is equal to this vector times T times V lambda V transpose T transpose times this vector, right? Now what can I am free to choose my transformation matrix, right? I can choose any transformation I like, right? I am going to choose whichever transformation simplifies my equation most or best, right? So if I choose the transformation matrix to be the matrix V transpose, then what happens? Then if I replace T by V, so I get, or T by V transpose, I get V transpose V lambda V transpose V, right? And we know that the matrix V, since these eigenvectors form an orthonormal basis, the matrix V is a orthogonal matrix, right? Since it's an orthogonal matrix, V transpose V got to be equal to the identity matrix, right? So eventually we get L phi is equal to del del y1 del del y2 lambda del del y1 del y2 phi, right? And notice that the matrix lambda is a diagonal matrix. So that is the biggest advantage we are getting, because now lambda is a diagonal matrix and we could bring it in this form. It is found that there are no cross terms, right? The cross derivatives there are no more cross derivatives, right? And we arrive at the equation, we only contain, there are no cross, so we only have derivatives with respect to y1 and y2, so there are no cross terms, right? Because we did this transformation, and because we chose our transformation matrix to be the matrix of the eigenvectors of my little coefficient matrix transpose, that's why we could get this simplification, right? So if we can do that, we get this uncoupling, right? We get rid of the cross derivatives, right? However, we still need to find lambda 1 lambda 2. Find lambda 1 lambda 2, well, that's just easy enough, because we have to find, we solve the eigenvalue problem, 2 by 2 eigenvalue problem, find out lambda, right? So we solve the eigenvalue problem. This is my eigenvalue problem, determinant of A minus lambda B, BC minus lambda equal to 0. Resultant, we get a polynomial. In this case, since it's a 2 by 2, the polynomial is a quadratic. We solve for lambda, we get that equation in terms of A and C, right? So you look at that equation, if you look at the term under the square root, it actually you can write it as a sum of two squares, right? You can write it as a sum of two squares, and since you do that, it is always got to be positive, right? it's also always got to be positive, and hence the eigenvalues are always real, which we already knew, right, because this is a symmetric matrix. So, its eigenvalues got to be real, but this is just we are seeing that. Now, consideration of the above equation gives rise to 3 cases. What are those 3 cases? Well, one case is when b square minus ac is positive, right. When b square minus ac is positive, you can see that the second term is larger than the first term, right, because this contribution b square minus ac is going to increase the term within the square root, right. So, at least one of the terms is going to be negative, right, while the other term for the positive sign is going to be positive, right. So, b square minus ac is positive, the second term is larger than the first term, hence one of the eigenvalues is positive while the other is negative. If b square minus ac is negative, the second term is smaller than the first term. In that case, we are guaranteed that both our eigenvalues are going to be positive, right. While if b square minus ac is equal to 0, we are sure that one of the eigenvalues is going to be 0, because a plus c minus a plus c, that is going to give me 0, and a plus c plus a plus c, that's going to be the positive eigenvalue, right. So, each of these cases correspond to a canonical form for the second order linear partial differential equation. When condition A is satisfied, when condition A is satisfied, the partial differential equation is said to be hyperbolic, right. So, that's just a definition, right. When that condition is satisfied, the partial differential equation is hyperbolic. What is that condition? Well, its eigenvalues are of opposite signs. One of them is positive, one of them got to be negative, right. How do we ensure that? We said lambda 1, the first eigenvalue is some square, and the second eigenvalue is the negative of a square, so it got to be a negative number, right. Recall that our original equation in the variables x1 and x2 was like this. It was L phi plus 2d phi x1 plus 2e phi x2 plus f phi equal to 0, right. The uncoupled expression for L phi after transformation to y1 and y2 has already been obtained. So, after we did the transformation that we did, we know that this L phi is going to be uncoupled, right. The term involving the second derivatives, the L phi term, the L phi contribution, it is more than one term, that is going to be uncoupled, that because the cross derivatives are going to vanish, right. So we have to, what we have to do, we have to transform this single derivative, the first order derivatives into the y1 y2 space, right. We have to do that, right, we have to be consistent, right. So, the remaining first order derivative terms need to be transformed using the same mapping, right, which was t is equal to v transpose, using that mapping, right. So, recall that del x1 del x2 is equal to t transpose del y1 del y2, and t is, we know, is the matrix of eigenvectors transpose. So, if my eigenvectors v1 1 v2 1 correspond to my eigenvalue lambda 1, and my eigenvector v1 2 and v2 2 corresponds to my eigenvalue lambda 2, then I can write it like this, right. So, once I do that, my entire original equation is now transformed in terms of my new variables y1 and y2, right. And what form does it take? Well, it takes this form, lambda square del 2 phi del y square minus nu square del 2 phi del y2 square, right. So, this is the L phi term that we saw earlier, right, that is the L phi term, and this is what happens to my first order partial derivatives when I write them in terms of y1 and y2 rather than x1 and x2, right. And then I pull out the coefficients of del phi del y1, I get this term involving 2d v1 1 plus 2e v1 2, right. And similarly, I pull out the coefficients of del phi del y2, I get 2d v2 1 plus 2e v2 2, right, plus I have the term f phi right. I have the term f phi, right, and then I do just some, again I want to replace this 2dv11 plus 2ev12 by mu d, 2dv21 2ev22 by nu e, right, and I replace small f by capital F, I get this equation, right. I get this equation at the bottom of the slide, right. Then I do a further transformation of variables. I say that I am going to replace y1, y2 by new variables alpha and beta, and this is how I define my alpha and beta. Alpha equal to y1 by lambda, beta equal to y2 by mu, right, and then I get this form, del 2 phi del alpha square minus del 2 phi del beta square plus d times first derivative plus e with respect to alpha, e times first derivative with respect to beta plus that term. Then we perform a third transformation. We replace phi by this function in terms of capital phi, right, and if we do that, we get a final form of this equation, right, the final form of this equation. And if you look at the term within brackets on the left hand side, it is of the same form as the wave equation, right. It is in fact the canonical form of the second order hyperbolic partial differential equation, right. It is the, so all hyperbolic partial differential equations can be obtained from this form, right, whether it is the Helmholtz equation, the wave equation, any hyperbolic second order partial differential equation you can get from this form. So this is the canonical form of the hyperbolic partial differential equation, second order linear partial differential equation, right. Similarly, we can do similar things, right. When b square minus ac is less than 0 and both the eigenvalues are positive, then the partial differential equation is said to be elliptic. It is an elliptic partial differential equation. If we perform very similar substitutions as in the hyperbolic case, we get this equation, del 2 phi del eta square plus del 2 phi del rho square plus k phi equal to 0, which is again the canonical form of the elliptic equation. So all elliptic equation, whether it be Laplace's equation or Poisson's equation, any elliptic equation you are going to get from this canonical form of the elliptic equation, right. And finally, for the condition when b square minus ac is equal to 0, that is when one of the eigenvalues is 0, the partial differential equation is said to be a parabolic partial differential equation. Again, performing substitutions very similar to what we perform for the hyperbolic case, we can get its canonical form, which is del 2 phi del rho square is equal to d del phi del eta, which is the canonical form of the parabolic equation. And this equation, if you look at that, that is very similar to the diffusion equation. So we looked at linear second order partial differential equations, we looked at the canonical forms. Next lecture we are going to talk about how do we get some of those physical equations. Maybe we will look at the wave equation, right, how do we get that equation, and then we will try to look at some simple analytical techniques for solving those equations, right, before actually moving on to numerical techniques. Thank you.